All right, so I'm going to start now. So this is our third review, and we're going to cover the exam 2 topics. Most of you guys did really well on that. I think the average was like 93 or something. So try to be quick. I'm going to try to get you guys in and out because it's a rainy, muggy Friday. I'm sure a lot of you guys are tired. So, all right, so what we're going to cover is undetermined coefficients, variation parameters, Cauchy-Euler method of solving homogeneous equations, and the definition of the Laplace transform. Now, the inverse and everything, that was covered in the third exam review. And I was thinking about adding another review, but I don't think there's going to be enough time. And also the Professor Brady, or whoever else is running it now, is doing a review on Sunday for all you guys from, I believe, 1 to 5. So you guys should go to that. He'll probably tell you more of like what's specifically going to be on the test because he's making a test. So he might have a little more insight than I do. All right, so without further ado, let's get started. And of course, ask questions if you need to. OK, so for all these different methods, these are second order differential equations, right? So that means you're going to have two constants. And you're going to solve, first you're going to solve the homogeneous equation using the methods we went over yesterday in the end of the review, which was if you have putting it to r's, and if you have two roots, complex roots, identical roots, and two different roots. We went over that. And you'll see those different homogeneous equations today. All right, so let's just start with an example, with undetermined coefficients being first. All right, so if you have y double prime plus 2y prime minus 8y equals, I'll put example, equals negative 32x squared. I'll make sure this one works. Yes. Because I had one on here that has like, when you can solve for the constants, you get a, b, and c. It's like 150 over 1,000. So there's something weird fractions, but I'm not going to do that. That's crazy. All right, so your first step in any of these, if you see something like this, your first step is to solve the homogeneous equation. Without even looking at the right side, regardless of what it is, we're going to set this right side to 0. When you're doing either undetermined coefficients, variation of parameters, or even when you see a Cauchy-Euler on the left side and something else on the right side. Our first step is always to solve the homogeneous equation. So we're going to go ahead and do that by first making this into, well, setting it to 0, the left side, minus 8y equals 0. And then we're going to turn this into r's. So for every, wait, I messed up. Yep, right there. So we're going to turn this into r's by every degree, every derivative degree. We're going to make the r into that degree. So second derivative would be r squared, and so on. So you're going to have r squared plus 2r plus 8 equals 0. All right, so now our job is to find r. So we're going to try to, what? Oh, cool. All right. So now our job is to find r. So we're going to do that by factoring this thing, right? We could do that. So we could FOIL it, for whatever the hell I call it nowadays. Minus 4 plus 4 minus 2. OK, so r plus 4, r minus 2 equals 0. Cool. So from this, you can see that there's two roots, because there's two different monomials, each of which are different. And they're easy to solve. This one's just r equals negative 4, and this one's r equals 2. So we have both of our roots. And they're two distinct roots, which is very important. So now we have two distinct roots. We can use the corresponding homogeneous equation for two distinct roots, which is very simply just, I'll write it over here, y homogeneous equals c1 e to the negative 4x plus c2 e to the 2x. So we're taking both of our roots, putting them into the e to the whatever, e to the r1x plus c2 e to the r2x. All right, so once we have that, we are done. That's probably going to be part A of the problem. Find the homogeneous equation, whatever. That's going to be the first part. So second part is where you're going to have to use your second order methods, your either variation of parameters or undetermined coefficients. Personally, unless they explicitly tell you to use undetermined coefficients, which they might, I would use variation of parameters. Because variation of parameters, you don't have to think about, oh, can I do undetermined coefficients for this? But everything on the right side, regardless of what it is, variation of parameters works. So I like that method better because it's really consistent and you can't mess up if you memorize all the different formulas and everything for variation of parameters, which we'll go over soon. All right, so here we're going to do undetermined coefficients. This one's pretty straightforward, undetermined coefficients. The right side, well, I should just write it. I'm going to write a chart real quick. Actually, I have that chart. So the right side of an undetermined coefficients equation It's used to model what our guess is going to be. Like I say that a lot of times where we need to make a template or a guess of what our answer is going to look like. So this right side, right now, it is a polynomial expression of degree 2, x squared. So it could be x squared. It's just a constant times x squared, right? So our guess for this, I'm going to write our guess right here. Then I'll write the chart over there, and then I'll continue with this problem. Our guess is going to be, or otherwise called our particular solution, which is this. The homogeneous plus particular is going to equal our total solution. Our particular guess is going to be, since this is a polynomial of degree 2, our guess is also going to be a polynomial of degree 2. But we'll write it like this, with undetermined coefficients. We don't know these coefficients, so they're undetermined yet. So ax squared plus bx plus c. So that's very straightforward, because you could technically write this plus 0x plus 0. And it's in the same form. Yep? No, it doesn't matter, because it's just the constant. The constant, it might be negative when we figure it out. Who knows? Yeah. And I think it's going to be, because once you're ahead of the game. You know. All right. All right. So once we have this is one of the guesses. So I'm going to write over here what the right side of the undetermined coefficients problem could possibly be. It doesn't necessarily have to be a polynomial of degree 2 to use this method. It could be a lot of other things. So I will write this down. So I'll write function on right side, function right side. And then I'll write guess. So if the function on the right side is a polynomial of degree anything, really, so I'm going to put, for example, 6x to the third. These are examples. 6x to the third, this would be ax cubed plus bx squared plus cx plus d. They wouldn't give you a third order one, because that's like ridiculous. You need to find 4 constants. It's a little crazy. So for any polynomial, this works. So if it's just 6x, it would be ax plus b. Another thing you use it for is e to the x. So if you have, example, e to the 2x, your answer would therefore be a e to the 2x. That's straightforward. It's going to be a constant times. And this stays the same. This number stays the same. E to the whatever x stays the same. OK, next one is with sines or cosines. So I'll just write cosine of x or sine of x. If you have cosine of x or sine of x, your particular is going to be a times cosine of x plus b times sine. Or, yeah, times b times sine, like that. So regardless of either you have a cosine or a sine or both, you're going to use this for your guess. So if you have something cosine plus something sine, your guess would be something cosine plus something sine. If you just have one cosine or one sine, this is still going to be your guess. Another thing to mention is if there's like 2x inside the cosine or the sine, the 2x would be the same in here. So that's a good thing to know. And another thing is, these are the main 3. You could group these together and have guesses that work for, suppose, a 6x cubed times e to the 2x, or 2 of these multiplied together. And I'll write an example of that. So suppose you have x squared e to the 2x. It's going to be the polynomial of degree 2, which would be ax squared plus bx plus c times e to the 2x. You don't need to add another constant, because this constant would just be multiplied in and become a constant. All right. So do those guesses make sense to everybody? There's a couple more. You could multiply this polynomial by sine, a polynomial by cosine, and then you end up with like 4 or 5 variables. Yep. Question?
My question was, there's occasionally that rule where you have to multiply by x.
Yes.
Remind me of the
OK. So his question was, once in a while in undetermined coefficients, there's a rule where you have to multiply your guess by an additional either x or t for it to work, because otherwise it would cancel out. The reason why that is because suppose you had, this is a good example. Suppose you had, this is your homogeneous, right? You have e to something x, so e to the 2x. If you had another e to the 2x on the right side of the equation, suppose instead of negative 32x squared, we had an e to the 2x, then you'd have to multiply your guess by an extra x, because you don't want your guess to have the same function as your homogeneous. Does that make sense? Okay, so why is that true? I don't know. I have no idea. But that's just the way it is. Maybe because you don't want to mix up your constants with some, I don't know. But if you have something in common, so if you have an e, that's not necessarily like, if you have e to the negative 4x and e to the 2x, that's different. But if you have the same e to the whatever x, or an x squared here or something, then it would be, you would need to multiply that by an x if it's the same. So I don't think I have an example of that, but if you can find one, I can do it. OK, so this is the chart. So now I'm going to go back to this problem. Here's our guess of ax squared plus bx plus c. So now our job, once we find this particular guess, is to take the necessary derivatives to plug it in to here, to y double prime, 2y prime, and minus 8y. OK, so this is already our y. Our y particular we're going to use as our y. So this, when we plug it in, this would go right into here. So 8 times, or negative 8 times all of that. So let's find our derivatives, which is fairly simple. It's a polynomial. So y particular prime, 2ax plus b. And then our second derivative is going to be equals 2a, just like that. All right. So now we're going to plug this in to our starting equation. All right. So we have y double prime, which is just simply 2a. So I'll write like an arrow. Right. Plug in. All right. So 2a, and then plus 2y prime. So I'm just going to factor this 2 directly into the y prime, because so we don't lose track of that 2 later on. So this would be 4ax now, 4ax plus 2b. And then you're going to have minus 8 times your y, which is your original particular guess. So that's going to be minus 8. I'm going to factor that in again. So it would be minus 8ax squared minus 8bx minus 8c. Just like that. And this is going to equal not 0, but the right side of the equation. So equals negative 32 x squared, just like that. OK, so is there any questions thus far on that? No? OK, cool. So with this, now our job is to try to find our coefficients. So we have one equation, 3 unknowns, right? Usually we have 3 equations, 3 unknowns to be able to solve this. But we can still solve this. Somehow this works. I really don't know why this works. But if you picture this in your head, where you have the polynomial of degree 2, so x squared plus 0x plus 0, and you are going to, next job is to compare the coefficients for your x squared on the right side to that of the coefficients of the x squared on the left side. And you're going to ignore everything else and make those two equal each other. So on this left side, the only thing that has an x squared is this negative 8a x squared. And on the right side, it's the negative 32 x squared. So we're going to ignore everything else and make those two equal to each other. So I'll write that right here. So negative 8a x squared equals negative 32 x squared. Just like that. All right, so as you can see, the x squares would cancel out. And if you divide this negative 8 over, you get 4. So a is going to equal 4. OK, so that's how you do it. So you do the exact same thing for both b and c is the next step. So for b, it's everything that has an x that has the coefficient of just a single x, x to the 1. So on the left side, that is 4ax, and you have an 8 or negative 8bx. So I'll do that right here. So you have 4ax minus 8bx equals 0, because 0 is the coefficient of the x to the 1 on the right side. All right, so this, we already know what a is, so we can plug that in. So we can put in 4 times 4 is 16, 16x. And we can move this, at the same time, we can move this minus 8bx over to the other side. So we made this equal to 8bx. And just like what you do with the a's, x's cancel out. And you can see that b equals 2. All right, b equals 2. All right, next step is with the constant. So the constant on the right side is going to be 0. The constant that's added additionally to this thing. And on the right side, or left side, sorry, you're going to have 2a plus 2b minus 8c. So I'll do that right on the bottom. So 2a plus 2b minus 8c equals 0. OK, so from the first 2 previous steps, we know that a equals 4 and b equals 2. So we can plug those in. 8 plus 4 minus 8c equals 0. Then you have 12 minus 8c equals 0. So that happens. So 12 equals 8c. So then 12 over 8 equals c, which is the same thing as 6 over 4 or 3 over 2. All right, cool. So is there any questions on that? No? Good, good. All right, so once we found our constants, we're basically done. What we need to do is plug these constants back in to our original guess, which is going to be our particular solution. So this is what we're looking for. And then we're going to add that particular solution to our homogeneous solution. All right, so I'm going to write the answer. Do we have room up there? Yeah, I'll write it on the top. So y total equals our homogeneous, which is going to have both of our constants. It's e to negative 4x plus c2. Can everybody see that? Yeah? OK. If someone said no, I probably would have just kept going, because I have nowhere else to put it. OK, so yeah, so y particular, add that. A is equal to 4. So we have 4x squared plus 2x plus 3 over 2. All right, cool. All right, so that's our total solution. Does anyone have any questions on undetermined coefficients as a whole? Any step in particular? Any guess that that doesn't relate to this problem? Anybody at all? No. Cool, good. All right, so I'm going to move on to, I wish I could move this up, but I can't, whatever. I'm going to move on to what's next? Variation parameters, my favorite method. All right. So I'm going to move this board down. All right. All right, so for variation parameters, like I said before, this method works with any second order differential equation that's in the form of a polynomial, such as like something y double prime plus something y prime plus something y equals something else. It works for all of them. There's a couple things you need to know and a couple things that we're looking for when we solve this variation parameters problem. So I'm going to write these things down first before we go through an example. So I'll just write v of p. Bless you. All right. So the first thing we're looking for is, of course, our homogeneous. And our homogeneous is going to be found the exact same way we do for undetermined coefficients. But we're going to use it this time to solve the particular solution. So we're going to use the parts of our homogeneous to solve the particular. And our homogeneous is going to be in the form of this. So y homogeneous equals c1 times y1 plus c2 times y2. So we're going to use these y1 and y2 later to solve the particular solution using the equations I'm going to write soon. So this could be the y1, y2 could be e to the x's, cosines, e to the something times cosine if it's a complex. And, or it could be like t e to the something if it's identical roots. All right, so next step is all right, so our particular solution. So yp, because you know our total solution is going to be homogeneous plus particular. Our particular is going to be in the form of v1, which I will explain what it is. v1 plus y1, or times y1, equals v2 times y2. OK, so the y1 and y2 are this exact same y1 and y2 from the homogeneous. And the v1 and v2 are found like this. There's actually no expression for v1. I don't know why. They made life more difficult, whoever invented this, because they have a v1 prime. So once we plug in what we need, we have to integrate it. So v1 prime is going to be equal to negative y2 times f of t over a divided by the wronskian, which I will write right here. I'll just write wronskian. Screw it. Where's my eraser? All right. A wronskian times. Not dot product, just times. OK. All right, so this is our v1 prime. There it is. Now v2 prime. v2 prime equals positive y1 times f of t over the same denominator, a times your wronskian. All right, so f of t is going to be the right side of the equation. So like, yeah, not the left side, the right side. It's going to be the right side. Your wronskian, you could do, there's different ways you can solve. You guys know how to solve the wronskian. You could do it's using y1 and y2. You could do your matrix methods or whatever. But I don't do that. I just memorize an equation. So here's our wronskian. Wronskian equals y1 prime times y2 prime, or y1, sorry, times y2 prime minus y2 times y1, which is the exact y1 prime, which is the exact same thing as your result when you do the matrix. All right, so does that make sense to everybody? I wrote a lot on the board. That makes sense? OK, one more thing, though. This a is the coefficient of the y double prime on the left side of your question. OK. And if you were to, if you had a coefficient and you were to divide it out, once you divide it out, whatever's in front after you divide it out would be most likely 1. That would be your y double prime. I mean your a. Sorry. OK. So let's get started on one. All right. So example, when you have y double prime plus y equals secant of t. All right. So the first thing to look for is, oh, can we use undetermined coefficients? No, we can't. Why? It's a secant. 1 over cosine. It just doesn't work. It's just, these are one of the secants, ln's, other weird functions that aren't the ones that were on the chart over there. Then you would use variation parameters, or even the ones on the chart over there, whatever you want to do. All right, so our first step, as always, is to find the homogeneous equation. We have to do this. This is really important now, because whatever we get will determine what we do next. So let's just turn this into r's and set it equal to 0. Equals 1. Don't be fooled. This is not a y prime. This is just a y. So you get r squared plus 1 equals 0. R squared equals negative 1. And then r equals plus or minus the square, plus or minus I. Yeah, because the square root of negative 1 is I. So plus or minus I. So that means complex, right? So we got to deal with all that cosines and sines and stuff. OK, so with this complex root, we can find the homogeneous, which is y homogeneous equals c1 cosine of just 1, because the coefficient of the I is just 1. So 1t plus c2 sine of t. All right. So that's the homogeneous. Pretty straightforward with that. OK. Now we need to locate, using these equations, looking at these equations, we need to locate our y1 and y2, which are just simply whatever's next to c1 and whatever's next to c2, respectively. So let's do that. So this is the cosine is going to be y1, and the sine is going to be y2. When doing the test, I always make sure I bracket it just so I know for later on, in case the whole board gets all messy and I need to see where I'm working. All right. So we have y1 and y2. So now the next step is we can plug it into v1 prime and v2 prime. So first thing we need to do from there is to find the wronskian. That's important. That's in both of the denominators for both of them. So let's find the wronskian now. All right. So w, wronskian, whatever, equals y1. So y1 is just cosine t, times y2 prime. So sine of t, the derivative of that, which is cosine. So cosine squared. A lot of you can see where this is going. Minus y2, which is sine t, times y1 prime, which is negative sine. So watch this. Boom. Look at that. The wronskian. What's the wronskian? 1. Good. 1. OK, because that's the super awesome trig identity that everybody told you about. Cosine squared plus sine squared equals 1. So we have our wronskian is equal to 1. Cool. So now we have a wronskian. We can now plug into v1 prime. So let's do that. So v1 prime is equal to, what do we got? We got negative y2. So that means negative sine of t times f of t. Now f of t is the right side of the original equation, which would be secant. So I'll write 1 over sine, or cosine. Yeah. Because you might see things might cancel. Oh, it's already negative tangent. Oh, my God. But something else might happen. Who knows? Actually, I don't think anything else is going to happen. OK. So Now we have on the denominator, we have a times the wronskian. So our a is whatever is the coefficient of our y double prime, which is going to be 1. And our wronskian, as we just found, is going to be 1 as well. So we have 1. So now this is going to equal negative tangent of x. We can actually leave it as, for integrating sake, let's leave it as this. OK. Now, do they give you an integration table anymore? Yeah? No? No? Some yeses, some nos? I hope they do. But if not, don't fret. They're going to give you, if they don't, they're going to give you easy integrals. Maybe a simple u sub thing like this. So our job right now is to integrate this in order to find v1, right? So we can integrate this by using a u sub, because we have a derivative of one of the other functions that's in here. So like sine and cosine are derivatives of each other, so we have that. And in a u sub, a very important thing to remember is always have the u on the bottom, because if you have the du on the bottom, it wouldn't work. You have 1 over du. You can't integrate that. You could try all day. It doesn't work. So let's make our u equal to cosine. So u equals cosine of t. And then our du is equal to negative, that's not negative, our negative sine of t. All right. So hey, that works out perfectly. You're going to end up with du over u. So it's the integral of du over u. And the integral of that is going to be natural log. So natural log of u, which is going to equal the natural log of, well, it's technically natural log of the absolute value of u, which is cosine of t. Why is the absolute value? I don't know. And that's it. So this is going to equal to v1 prime. And you don't add you're integrating, but you don't add the plus c at the end, because both of your constants for the second order problem are taken care of in your homogeneous, where you have c1 and c2. So it's always a good thing to remember. Don't add any extra constants where you don't need them. Wait, this is v. Oh, yeah, sorry. That's v1. That's v1. We just did the integral. So. All right. So we have v1. Good. So now we're going to find v2. So we're going to start off with v2 prime. Same exact thing. A little bit similar, a little bit different. All right. So you have y1. y1 is cosine of t times f of t, which is 1 over cosine of t. You can see what's going to happen. Over the same denominator, which is 1, a times the wronskian. So cosine over cosine is 1. This whole thing's 1. Integral of 1. Cuomo, integral of 1. X, good job. So we got x. That's it. Oh, wow, I'm an idiot. OK, t. T equals v2. All right, good. All right, we got that. All right, so now we have our v1 and v2. Our job is to literally just plug everything into the particular, which is this. And then add that to the homogeneous. So let's write the answer. I'll move this board up a little bit and write the answer right here. So our y total is equal to our homogeneous, which is c1 cosine of t, plus c2 sine of t, plus our particular, which is v1, which is natural log of all that stuff, cosine of t, absolute value, bunch of brackets and all that good crazy stuff, times what? Times y1, which is cosine, plus v2, which is t. That looks like a t. I should make that a plus. T times our y2, which is sine. OK. So that's your answer. If they give you initial conditions on something like this, I hope they don't, because then you have to integrate, or not integrate, derive this entire thing, because they would have to give you 2 initial conditions because you have 2 constants. They'd have to give you y of something, or y of t, y of 0 equals 0, and y prime of something equals something else. Yeah. So any questions on variation of parameters? No? Pretty good? If you guys have any questions on specific problems, I'll even, because this is going pretty fast, I'll stay after and like do a couple more if you want, off camera, do a secret show. All right, so I'm going to move that up and then take this one down. So look, we're almost we're basically almost, what time is it? Almost done. That's crazy. We'll be done in like less than an hour, right? Isn't that awesome? I had 2 text messages from unknown numbers. Cool. All right. All right, so now we did variation of parameters. Cauchy-Euler. Right, Cauchy-Euler, good old Cauchy-Euler. All right, so Cauchy-Euler, or Cauchy-Euler, whatever, two scientists, two mathematicians, they got together and made this crazy homogeneous stuff. I can't even imagine like where they came up with this. Because probably like they probably invented, they probably like were at a conference with like the other homogeneous, conference about homogeneous, whatever. And they were like, what if you put x squareds and x's on the left side also? And then the guy's like, shit, we have to go back and do more stuff. We'll work for another 40 years to figure that out. And then they came up with this. So really what it is another way to solve the homogeneous. Just the left side, not particular. So sometimes you might have the left side with Cauchy-Euler, a bunch of x's, x squareds, and all that stuff. On the left side with a particular looking thing, either variation of parameters or undetermined coefficients on the right side as well. But you do the exact same thing. The only thing that changes is the way you find the homogeneous equation, which is the method of Cauchy-Euler, which I'm going to explain right now. All right, so let's see. So Cauchy-Euler, it's not Euler, it's Euler. He was German, so it's Euler. All right. So the general form, so the form is ax squared y double prime plus bxy prime plus cy equals f of x. Okay. So f of x is going to be whatever on the right side of your equation. It could be 0 if you're just finding the homogeneous, or you make it 0 regardless because you find the homogeneous. All right, so some things that could happen with this form for them to confuse you. They can put an x cubed, an x squared, and an x. In that case, you just divide out by x. But then this changes. If this is not 0, that changes. What else? They can put, I don't know, whatever. They'll figure out something out. They're confused. Something you could divide out. If it doesn't look like this, think you have to divide something out or even move something over. I don't know. You'll see. You'll see. All right. So that's the form, right? So what do you do with this form? What do you do with your a's and b's and c's? Normally, if these x's weren't here, you just do ar squared plus br plus c. But now you don't. Now you do a little bit different. So your root formula, when you do transform it to r's, but it's going to look a little different. The ar squared is going to stay the same. But in the middle, with the br would now become plus parenthesis b minus a times r. That's the only difference. Then it's going to be plus c. And that equals 0 because you're trying to find the homogeneous. OK, any questions on this? That's just memorize, just know it, whatever, just know it. So you have b minus a times r in the middle. OK, so once you solve that, you're going to have 3 different cases, just like for regular homogeneous. You're going to have two different roots, 2 identical roots, or 2 complex roots. So if you have, I'll write that over here. So if r equals 2 real roots, like -2 and 2 or something like that, you're going to have y equals c1 x to the r1 plus c2 x to the r2. OK, something like this. This is the main case where your question before with when you're doing undetermined coefficients, when you need to multiply the guess by an extra t or an extra x. So if you have on the undetermined coefficients, when you're doing that, if you have a polynomial such as like 10x squared on the right side, and you find this something x squared as your homogeneous, you would need to multiply that undetermined coefficient answer guess by an extra x or t. That's because you don't want this to look the same. So this is where this is more prevalent, because you have polynomials here as well. OK, so I hope that made somewhat sense. I don't think I ever make sense. All right, so if r equals 1 repeated root, or 2 identical roots, whatever you want to call it, 1 repeated root, you're going to have very similar, but y equals c1 x to the r plus c2. And instead of multiplying it by x, like we do for regular homogeneous, you multiply it by natural log of x times x to the r. Just like that. So I'll put stars next to these. And then our third case is where you have if r equals complex, which is in the form of a plus or minus bi, like that, you're going to end up with y equals c1, or I could just factor this. Hold on. I'll write it a little neater. So instead of having, you know how you have your e to the alpha x on the outside of it with the regular homogeneous, this is going to be x to the alpha. So x to the alpha times c1 cosine. Instead of beta x, it's going to be natural log of, wait, no. Yes, but I didn't write it. I'm going to write it a little better than that. So it's going to be cosine of beta times natural log. So cosine of beta times natural log of x. Plus, you have your c2 times the sine of beta times the natural log of x. Just like that. And another parenthesis. Wait, yeah. OK, cool. All right, cool. So that's your different root. That's your different scenario, different cases. Any questions on those? No? All right, cool. So now I'm going to do an example. All right, here's one. I'll do this one. It was a little difficult. I'll do it. All right, so suppose you have this example. 9x squared y double prime plus 15xy prime plus y equals 0. OK, so what do? We do what we know to do, which is all this stuff. So first thing is to find the r's, find what r equals using this equation, this modified equation. So this is going to be 9r squared plus, now we're going to have b minus a. So b is 15, minus a is 9, or minus 9 is going to be, what was that, 6? 7? 7. I know math. All right, so 7r plus 1. It's 6? Wow. Yeah, it is. It's 6. Sorry. Whoopsie. I can't do simple math. All right, so 9r squared plus 6r. That was embarrassing. Wow. OK. So plus 1. This is going to equal 0. So now we need to find, we could factor this out. Can we? No. We can't do it directly. But let's do, you can, I don't like having things in front of there. I'm just going to go right to the quadratic formula because I forgot algebra 2. So I like quadratic formula. So, OK. So r is going to equal, what is it? Negative b, negative 6 plus or minus the square root of b squared, which is 36, minus 4 times ac, which is going to be 4 times 9, over 2a, which is going to be 18. Look, 36 minus 36, 0. Cool. There's going to be negative 6 over 18. All right, cool. That makes sense to everybody? Yeah, if there's something like this, I mean, yeah, some of you guys were like, oh, maybe you could factor that. You probably can, whatever. I don't want to think about it. You just, if you're going on a test and you know how to solve this using a quadratic formula, which is right all the time, it's better than like guessing and checking with like, oh, 9r and 9r something or whatever. So we got an answer. It's one root because this square root thing cancels out. You're going to have 36 minus 36 is 0. So square root cancels out. You only have one answer, which is negative 6 over 18, or negative 1/3. So since we only have one answer, we're going to use case 2, where you have one repeated root. So for that, our y homogeneous is going to equal c1 x to our root, which is going to be negative 1 over 3. And then we're going to have plus c2 times the natural log of x times x to negative 1 over 3. Just like that. Another way you can write it is c1, if you want to be an overachiever, c1 to the c1 over cube root of x, whatever, or this thing over the cube root of x. But that's the same thing as that. OK. So is there any questions on Cauchy-Euler? Yeah. Yeah. That's a very good question. So he asked, is the when you're doing undetermined, when you're doing variation of parameters, sorry, is the A this whole thing or just the 9? I think there was a case where I did have a problem like this and it was the whole thing. And then like I tried it on some other problem, it was just the 9. I think it's the whole thing now. I think it's the whole thing. So do we have an example we could like figure this out like right now? But I'm pretty sure that the whole thing in front of the y double prime would be your A. Yeah. Yeah. I mean, we could whatever. Whatever. I'm pretty sure, like 85% sure it's that. Okay. Good question. Very good question. All right. Is there any more questions of that nature? Okay. All right. Cool. So I am going to do some Laplace. I'll look into that. I'm going to, for 100% clarity, I'll look into that, and I will post it on the Facebook group because I'm like 85% sure about that. All right. The particular part? Yes. So yeah. So f of x, in this case, f of x is 0. So, but this is the form that you're going to get for when you're going to use Cauchy-Euler. But it only is a method to solve your homogeneous equation. Yeah. Okay. All right. So now we are almost done. Now we're going to do some Laplace. Okay. Definition of Laplace. Good thing I'm only doing definition. I don't want to do inverse. It'll take like 3 hours. And it's raining and I'm tired. All right. So the definition of Laplace transform. So it's pretty easy. It's just a definition. That's exactly what it is. Something to know. Definition. And then means something. So definition. So Laplace definition is literally the integral from 0 to infinity of e to the negative st times the function f of t equals the Laplace of y. Okay, or yeah, where y equals f of t, or whatever, the function, the Laplace of the function. All right, so that's it. So when we do an example, usually they give you a piecewise example. So example is find the Laplace transform if f of t is equal to, you have 0, 3, and 0, of 0 less than or equal to t less than 2, 2 less than or equal to t less than or equal to 5, 5 less than t. That. All right, so we're finding that, the Laplace for that. So since we're given bounds from 0 to 2, different domains, 0 to 2, 2 to 5, 5 to infinity, we're only going to do the Laplace of the middle part because the Laplace here is 0 and the Laplace here is 0. Because if you multiply these, put these derivatives in here, that's going to be 0. So we don't need to find that. All right. So let's do that. So we only have to focus on the middle part. Okay, so let's literally just write the equation. So instead of from the integral from 0 to infinity, since we already have bounds in the domain, it's going to be from 2 to 5. Because this is the domain we're going to focus on. Okay, so and you can even write it as from 0 to infinity. That's where the function goes from. But you're later going to have to break that down into 3 integrals anyway. This one being 0, this one we're going to have to focus on, this one being 0. So might as well just cut to the chase and just do 2 to 5. 2 to 5 of e to the negative st times f of t. F of t is equal to 3. We can put that 3 on the outside. It's a constant. Times dt. All right. So this integral, e to the negative st, is going to be e to the negative st over negative s. and then we're going to have the 3 in there from 5 or 2 to 5, just like that. So we're going to plug those boundaries in. So we plug in the 5 first. We'll do 3e to the negative 5s. And we're plugging these values into t, not s. S is what we're looking for, or s is what we need the answer to be in terms of. Because Laplace transforms, we are taking something with t's and making it into something with s's. All right. So we have that, and then over negative s minus, plug in the 2, 3e to the negative 2s over negative s. Now we could just take that away, take that negative away, put it right there, put positive, and we have that. All right, so if you were to refer to your Laplace chart, which they're going to give you, you could turn this into the equation of the answer, I think. But I think this one's a little more complicated. But normally, like if you could go from Laplace back to inverse Laplace, so you would take the inverse Laplace of this if they give you something easy, and then you'd be able to find the function using the Laplace chart that they give you on the back of the test, which I think that was covered in your exam 3. And there's a lot of stuff you can do with that. I have notes on that in the notes that I posted online. So, yeah. OK, so is there any questions on that at all? No? All right, that's it, really. That's quick. Anybody want sauce? It's just tomato sauce. It's probably really shitty. So, yes.